Today in this video, let us learn about forward biasing of PN junction diode. Now let us see what are the topics that we are going to discuss today. The topics are: what is meant by biasing, the operation of the PN junction diode in forward bias, how to draw the VI characteristics of the PN junction diode in forward bias, and finally quiz. There is a quiz at the end of the video, so please do watch the video till the end. Now moving on to the topic, first let us see what is meant by biasing. Now let us see how we can define this biasing. Biasing usually refers to a fixed DC voltage or current applied to a terminal of an electronic component such as diode, transistor or vacuum tube in a circuit in order to establish proper operating conditions for the component. That means biasing refers to a fixed DC voltage or the current that is used to provide the proper operating conditions for the components. Now let us see how we can define the bias voltage. The bias voltage is the amount of voltage that an electronic device needs in order to power on and to function properly. So if you see here, this is the bias voltage which is plus 2 volts. And this is the amount of voltage that an electronic device needs in order to power on and to function the circuit properly. Now let us see the forward biasing of the PN junction diode. In the forward biasing of the PN junction diode, the positive terminal of the voltage potential is connected to the P-type semiconductor while the negative terminal is connected to the N-type semiconductor. So if you see here, this is the forward biasing connection in which the positive terminal of the voltage potential is connected to the P-type semiconductor, whereas the negative terminal of the voltage potential is connected to the N-type semiconductor. And to limit the current, practically a current limiting resistor is connected in series with the PN junction diode. So if you observe here, this is the current limiting resistor which is connected in series with the PN junction diode in order to limit the current. And this is a forward biased connection circuit in which the positive terminal is connected to the anode terminal of the PN junction diode while the negative terminal is connected to the cathode terminal of the PN junction diode. And this is the R, which is the current limiting resistor connected in series with the PN junction diode. Now let us see the operation of this forward bias PN junction diode. When the PN junction diode is in the forward bias condition, then if the applied voltage is less than the barrier potential voltage, then there will be no conduction taking place between the P-type and the N-type semiconductors. So if you see here, this is the forward biased PN junction diode in which the positive terminal of the battery is connected to the P-type semiconductor, whereas the negative terminal of the battery is connected to the N-type semiconductor, and this is the current limiting resistor. Now in the case of the PN junction diode, if the applied voltage is less than the barrier potential voltage, then there will be no conduction taking place between the P-type and the N-type semiconductors. This is the P-type semiconductor and this is the N-type semiconductor. So we know that in the case of the P-type semiconductor, the majority charge carriers are the holes, whereas in the case of the N-type semiconductor, the majority charge carriers are the free electrons. And this is the depletion region between the P-type and the N-type semiconductor. Now when the applied voltage becomes greater than the barrier potential voltage, then the negative voltage of the barrier pushes the free electrons against the barrier potential from the N region to the P region. So now if this applied voltage is greater than that of the barrier potential voltage, now this negative voltage pushes these free electrons from the N region to the P region. Similarly, the positive voltage of the battery pushes the holes against the barrier potential from the P region to the N region. Now similarly, the positive voltage pushes the holes which are the majority charge carriers in the P-type semiconductor towards the N-type semiconductor. Now these electrons combine with the holes which are pushed in the opposite direction. So now these electrons combines with the holes which are in the opposite direction towards the junction. Now hence up to this voltage point there will be zero current flowing across the circuit. Then a little increase in the external voltage causes a high current to flow across the diode. Now if we increase the external voltage, then a high current starts to flow across the diode. And the voltage at which the diode starts conducting is called as the cut-in voltage. Now the application of the forward biasing voltage on the junction diode results in the depletion layer becoming very thin and narrow. So now if you observe here, the application of the forward biasing voltage on the junction diode causes the depletion layer to become very thin or narrow. That's why in the case of the forward biasing PN junction diode, there will be narrow depletion region which represents a low impedance path through the junction, thereby allowing a high current to flow across the circuit. And this current is the forward current, which is the combination of the electron current and the hole current. And the point at which this sudden increase in the current takes place is called as the knee point. So since the diode can conduct infinite current above this knee point, it effectively becomes a short circuit. Therefore, a resistor is used in series with the diode to limit the current flow. So this is the resistor which is connected in series with the PN junction diode in order to limit the infinite amount of current that is flowing through the circuit. So this is how the forward biasing of the PN junction diode is operated. Now let us see how to plot the VI characteristics of the forward bias PN junction diode. The response of the PN junction diode is indicated by its characteristics curve, which is called as the VI characteristics curve. So this is our forward bias PN junction diode, in which the positive terminal of the battery is connected to the anode terminal. Negative terminal of the battery is connected to the cathode terminal of the PN junction diode, and this is the current limiting resistor. And the VI characteristics curve is a graph plotted between the voltage applied across the PN junction diode and the current flowing through the diode. So from the figure, if the applied voltage to the diode is denoted as V, while the voltage across the diode is Vf, then the current flowing in the circuit is called as the forward current and it is denoted as If. So if you observe here, in the case of the forward bias PN junction diode, the applied voltage is denoted as capital V, and this is our diode, and the voltage across the diode is represented as Vf, and this is the amount of current flowing across the diode and it is represented as If. Now the plot of graph between the forward voltage Vf against the forward current If is called as the forward characteristics of the PN junction diode. Basically, the forward bias characteristics can be divided into two regions. So if you see here, this is the characteristics curve for the forward bias PN junction diode and it is for the silicon diode, which is plotted between the forward voltage Vf and the forward current If. Now the two regions are, the first one is the region from O to P. As long as the value of the forward voltage Vf is less than the value of the cut-in voltage V gamma, the current flowing through the diode will be very small. So, as long as the forward voltage Vf is less than the cut-in voltage V gamma, the amount of current flowing through the diode will be very small. So that is represented over here. This is the point O and this is the point P. So, since it is the silicon diode, the cut-in voltage is 0.7 volts. So, up to the point of the cut-in voltage, the current flowing across the PN junction diode will be very small. Practically, this current is assumed to be 0. So up to here, the current is practically taken as 0. The next region is from P to Q. As the value of the forward voltage Vf increases towards the cut-in voltage V gamma, then the width of the depletion region gets reduced. So when the value of the forward voltage Vf exceeds the value of the cut-in voltage, then the depletion region becomes very thin. So at this point, the forward current If suddenly increases exponentially. So if the value of the forward voltage exceeds the value of the cut-in voltage, then there will be a sudden increase in the current. So this is the exponential increase in the current, and this is the region from P to Q, where there is an exponential increase in the current across the PN junction diode. So the point P after which the forward current starts increasing exponentially is called as the knee voltage. So this is the point P, which is referred to as the knee voltage. And the important point to be noted is the forward current If is the conventional current, hence it is treated as positive, and the forward voltage Vf is also positive. So hence the forward characteristics are plotted in the first quadrant. So this is the first quadrant over which the forward characteristics of the PN junction are plotted. So this is how the forward characteristics of the PN junction are plotted. Finally, there is a quiz for testing your knowledge. Click on the link below so that you will be directed to the Google form quiz. Hope you like this video and understand the concept of what is meant by biasing, the operation of the PN junction diode under forward bias condition, and how to plot the characteristics of the PN junction diode under forward bias condition.